All right, it's my pleasure to introduce Kelly Smyth. She's the Associate Director of Lab Planning at Genesis AEC, leading highly technical laboratory and research facility projects. She brings expertise in both small-scale and campus-wide planning with a focus on life sciences design. Known for her technical excellence and collaborative leadership, she helps deliver adaptable, high-performance spaces that support research and efficient workflows. And today she's going to be talking to us about strong foundations, building understanding through lab programming. Kelly, the floor is yours.
All right, thank you so much, Scott, for the kind introduction. We'll get through these slides, so please do not read all of this, but this course today will be all about what comprises the lab programming phase, how to develop a programming process and undertake effective lab programming as part of the design process, and why these activities are so important and foundational to effective lab design outcomes. Take a look at our learning objectives up here, and we'll get started. So this presentation is all about the power of good questions, and I'd like to start with a question. What would you like for dinner? Or perhaps lunch, since that's coming right up here. But when I ask this question of my 6-year-old, I'll get one of two answers: pizza or mac and cheese. But if I ask better questions, like would you like quesadillas or hummus wrap, would you like that with broccoli or carrots, and I take into account what vegetables she's currently eating, what's in my refrigerator, and what I would also like to eat, it helps us get to a happier, healthier meal for everybody. So good questions do heavy lifting, and in lab programming, the questions we ask and how we ask them, when we ask them, can really make all the difference in delivering a project that works, or one that doesn't. So I don't mean to imply that our clients are like 6-year-olds, mostly. But I do think the analogy holds in a few significant ways, and there's some parallels between the programming skill set and the parenting skill set. One, every project is different, and every client and situation comes with specific nuances that we need to get to know. There'll be different considerations across multiple clients and multiple sites, such as those broadly described here. And secondly, as lab planners, we really need to navigate that line between needs and wants. So what users request and ask for has to be filtered through those business drivers and the project-specific realities and the constraints. So our job as planners is to help everyone get to creative, safe, and effective solutions that are agreed upon by everyone. The other context, in addition to the organizational culture and the site, is understanding the scientific context of the projects that we undertake. And specifically the life sciences research to commercialization pipeline that is shown here. We are familiar at Genesis with lab types across this continuum, and understanding which stages are involved on a project or where we are in this life cycle can be very informative and helpful to contextualize. The continuum is also not just a timeline, but really parallels the trajectory of scientific knowledge from pure curiosity through structured inquiry to applied intervention in the world. So the lab types and the ways of working and scientific approaches vary along that pathway. Early research and discovery, as we've been talking a lot about today and highlighted in the keynote, it's open and exploratory, and the spaces similarly want to be collaborative and open. So spatial organization and design concepts often reflect that. Flexibility for the changing needs is very desirable, and space is more fluid and interactive, so the adjacency and the flows might matter more than strict controls. When we're looking at spaces supporting preclinical and clinical testing, these become increasingly process-specific with stricter controls, and then working into commercialization, where we have CGMP manufacturing labs and spaces, these are The strictest of environments and the spatial organization priorities start to reflect that with prioritizing the process and the ability to maintain our area classifications and spatial segregations required, and prioritizing quality control and documentation. So this scientific context and the site and business drivers context, these all help inform project understanding, which we can understand as the first phase of the programming process, followed by data and input collection. So today's session is really focusing on this upfront work. And these problem diagnosis and criteria definition activities really lay out the puzzle pieces that are put together in the subsequent planning phases and tested to reinform initial understanding in this iterative design concept. So by the time we wrap up today, I really hope to leave you with a practical framework for undertaking this programming phase, which will include questioning the questions, so confirming what you think you already know going into a project, defining the lab design basis, so identifying those key safety and major facility impact criteria, and managing the information, so documenting it effectively, and representing the science needs to the overall project team, as well as the constraints and realities of the project back to those science end users. So this takes a specific skill set for sure, but programming also takes a mindset and an attitude. We don't know exactly where we're going, but we need a navigator. So this means staying organized and having a plan, detailing out the project schedule and understanding the milestones that you need to meet to deliver, to meet the project schedule, and setting up a detailed meeting schedule, as well as identifying clear roles on the project. So what data is needed, by when is data needed, and from whom. But we need to remain flexible. So we've talked about how things change. So flexibility is really, really key. New information, needs, and conversations will emerge through the process, and that's not a flaw. We need to reroute, and that's part of programming, because programming is all about discovery. So how do we undertake these discovery activities? The project understanding and data collection activities. I like to think of these activities broken into 4 categories, with the pre-design review activities and priority mapping, informing project understanding, and then the data collection work that needs to happen through programming sessions with interviews and questionnaires of lab users, and then the physical data point collection. So let's dive into each of these tools, starting with the confirmation and review. So this is about being prepared coming into a project kickoff, and as a designer and as an architect, doing the homework and really digging into the design brief or an RFP or whatever baseline documentation and project understanding you've been given. Important not to take this at face value, but treat it as a hypothesis, read it critically, and look for gaps and flag assumptions to reconfirm those. This is where background and historical knowledge of clients can be very helpful as well, understanding client-specific standards to understand how those might need to apply to specific programs. As an example, or a specific example in this topic, on a small project recently that involved a small lab component to a larger renovation project, the facility management team had documented as part of the design brief that the small lab that was supporting MRI prep work did not have BSL-2 ventilation or design requirements. But in talking to users at the kickoff, they expressed they were following some BSL-2 protocols with their work that included tissue handling and tissue storage. So flagging that right away for reconfirmation and bringing environmental health and safety into the conversation to align on that was a very important thing to do, so that we're not building the design on a faulty foundation. So next, I want to talk about priority mapping. So this is defining the business case. And this is the conversations and planning that needs to happen with leadership, project leadership, and not just the scientists. We build priority mapping at Genesis into every project that we do. So it can be undertaken as a separate visioning exercise or part of the project kickoff, but the business case isn't considered separate from the design. It's really integral to the design basis itself. So what is the organization trying to achieve? What does success look like for the facility and for the project? And what are the potential challenges that key stakeholders foresee? These can help bring priorities and key topics to the surface. Budget and schedule are always present factors that define the basis of any project and will direct decisions. So understanding how those influence and are factors in the priority mapping exercise is really key. So priority mapping gives you a documented foundation as well that you can return back to throughout the project. So when things do change or somebody wants to change direction, you have a reference to return back to and understand how that will impact the rest of the project. So now for really digging into the data collection topics, and this being one of my favorite parts of the process, which is talking to the scientists and really getting into the program in terms of the process and the people that are going to use the space. So user interviews are really where the science lives, and they require a particular kind of skill. You have to be curious enough to let people go deep on topics and disciplined enough to keep the conversation moving forward. A few tips shared here. We like to begin with the background. So how does this project that we're undertaking connect to their work? What is the scientific focus of the group that you're speaking with? What is their area of research and the ways of working? People love to talk about science, and I love to hear about it, so we want to let them talk. And build on the questions as you go. So start with general requirements, adjacencies, and overall questions, and then move into more specific topics, like their equipment needs and utility needs, and specific space requirements. And to that same point, questionnaires need to be catered to the project and to the type of science that's involved, and they should be guiding documents, not inflexible forms. So going into programming sessions, I like to think of the programming questionnaire a little bit more like a choose-your-own-adventure book rather than just a straight narrative or checklist. We practice agility and flexibility in that same vein to take in new information and allow certain topics to expand or other topics to retract for what's relevant. And then lastly, document everything from these sessions. So the responses to our lab programming questionnaires become part of the institutional memory of the programming phase and are something that we continually refer back to as the design continues to develop. And in this process, questions will lead to more questions, and that's not a problem. That's definitely the process working. All right, so now to dive into the physical data point collection. Physical surveys, lab equipment lists, and equipment surveys. This is where we gather a lot of critical data. And also lab tours and walkthroughs and site observations can reveal things that conversations don't. So how space is really used, adjacency problems, these all show up in the field. So all of these programming activities, the review, priority mapping, interviews with users, and the physical data points are about identifying and pulling in criteria that inform the lab design basis. One of the most important things that I'd really like to leave you with today is that lab types do not exist in a simple list. The list is endless, right? But they do exist in this multidimensional framework. So every lab program and project will sit at the intersection of these criteria dimensions. So the business case that we discussed, including site and context, and the building code and regulatory compliance layer of those factors, as well as the safety and hazard classifications and the scientific requirements. So when we undertake programming, we are probing all of these dimensions simultaneously and identifying the key criteria of each. So within the regulatory and code compliance realm, this category encompasses the codes and standards that may be established by our federal and state bodies. Identifying this framework at the very beginning is critical, as building code-driven criteria informs project basics like construction type, occupancy, allowable height and area, and considerations for allowable quantities of hazardous materials as well is something to identify and understand early. CGMP requirements will also have major impact on space planning in terms of segregation of spaces, and high-level cost considerations as well for the finished selections and equipment protocols. So identifying where these apply in the project is critical. Moving into safety and hazard classification, so these are similarly foundational and overlay with that regulatory layer. Examples include biosafety and animal biosafety, which pertains to containment for reduction or elimination of exposure to hazardous agents, and radiation safety, which pertains to the minimization of radiation exposure for workers and the public, as well as minimization of the risks related to strong magnetic fields with high impact equipment like NMRs or MRIs when we're dealing with imaging programs. The image here depicts a hot cell being installed in place, which is a heavily sealed containment chamber for the handling of radioactive materials. And as you can see, it's comprised of an immense amount of lead. So the shielding requirements here indicate very early structural impact and structural assessment that needs to be undertaken and understood. So this is an example, just one of many of these kinds of early impacts that get identified with the safety layer. Industrial hygiene pertains to the design strategies and containment measures that may be required for potent compounds, so other chemically or biologically derived hazardous compounds, and how those, if those are present in the environment, how are we dealing with them, or what measures might need to be taken. So all of these topics can directly impact major spatial organization considerations and criteria, and even the need for additional support systems or spaces with biosafety level considerations. We may need a decontamination autoclave as part of the facility, or we may even need an effluent decontamination system, or fire water may need to be collected. These are major things to bring up at the beginning of the project. They're not surprises that you want to have come up later. So this brings me to the last thing that I want to cover with you today, ensuring that programming, well, first I'll briefly talk about the scientific overlay, of course, because this is very important as well. Apologies. The science discipline and the methods and the equipment and the space. So how do these overlay with those safety classifications, and what are the needs of the space related to the science itself? Is it an equipment-heavy lab type supporting bioanalytics, or do we want a more open environment with wet lab? Dependent upon the types of science the lab is housing, these of course have major impacts to process utility requirements, electrical power, infrastructure considerations, as well as tying back to those safety triggered design impacts. So these things all intersect and have multiple overlapping considerations that imply major considerations around the design approach that's going to be unique to each project. So that will bring me to the last thing which I'd like to cover with you today, ensuring that all of this work is properly planned for and built into the schedule. So we have here just two high-level conceptual project timeline comparisons. And when dedicated time to the lab design basis definition and programming is not built in up front, it does cause disruption to the later phases of design when it is more complicated to incorporate and can require rework. So for example, like an autoclave popping up that's needed, right? Where is it going to go? How does it, we can see how it's problematic to have those surprises happen. So uncovering those things and leaving no stone unturned, we want to push that towards the beginning of the project, where it is least costly and most impactful. So the informed design approach invests more time in pre-design, the visioning and the programming, but results in that smoother trajectory as well as better documented and aligned design basis decisions with overall gains to the schedule at the end of the day, ideally, and better delivery outcomes. So there's a quote on the slide here that I really love. Time spent in sharpening the axe may well be spared from swinging it. You may have heard other versions of this out there. Abe Lincoln knew it to be true, reportedly, 100 years ago, and it's definitely still true today. So pre-work prevents rework. Before we end, I just want to go over what do the outputs from a successful programming phase look like, or what are some of the documents and the programming artifacts and living documents that we can expect here. So I refer to them both as artifacts and living documents because some of these documents capture decisions made and clearly convey the data collected, but as a static record of the programming decisions, and inform the next phase of layout development. So in the example here of a bubble and adjacency diagram, this looks at multiple lab groups and their spatial and working relationships to identify key adjacencies that will then inform the actual conceptual layout. Once we have clearer understanding of the specific space needs. Head counts can be tabulated and recorded as part of programming, and using benchmark space requirements based on head count, you can see the relationship here in terms of identifying those target program areas. So these also serve as important pieces of the documented data from programming. A program space list, once that is determined, can also reflect the categorized space types needed. Some other examples here. Room data sheets document specific requirements and characteristics specific to laboratory room types and can be used to document at varying levels of detail room finish requirements, furnishings, HVAC, piping, and infrastructure needs. Lab cards work to provide similar information, but as well as providing generic layouts that are site agnostic and help visualize and confirm the spaces needed, the physical space needed and the working space required for any given program. So determine as part of your project initiation the utility and applicability of each of these types of tools for any given project, and they will all serve you very well throughout the rest of the process. So thank you very much for your time and attention today. I'd like to leave you with 3 things. Plan for dedicated programming. Don't let this get squeezed. The upfront investment will pay off. And second, involve a lab planner early in the process with the knowledge and background to build the right programming roadmap for your project. This will look different for every project, and you need someone who can read beyond the initial ask and ask the right questions moving forward. Third, lab planning is a communication specialty. It's not just a design specialty. We want to make those connections between the facility, personnel, and administration, the scientists, and the designers to remove that tension that was brought up in the keynote today.